All right, guys, I want to go through one more general gas law College Board problem. So this is one from a past AP exam as well. And I kind of want to see where we are and how we're doing. If you haven't, take a second and just kind of pause. Here's the full question so that you can answer it and see where you are. Okay, so hopefully we paused and actually worked through this problem. Now, let's work through it together. Calculate the total pressure in ATMs of the gas mixture in the cylinder at 298 Kelvin. So total pressure. Okay, also notice that we are not at STP, so we can't just use that conversion. We have to do something else. And total pressure would include all moles or all substances present in the mixture. Well, we have nitrogen and oxygen present in this mixture. Okay, and because we're not at STP, we're going to end up using PV equals nRT, okay, which means we are trying to calculate pressure. We're already given volume, which is our 5 liters. N is something we can get. R is a given, and temperature we're told is 298. So moles is what we need to work on for right now. Okay, well, we're given grams of 2 different species. We can find moles pretty straightforward. Okay, so we take our 24.5 grams of N2, and we're going to divide that by the 28.02 grams, which is the molar mass of nitrogen. Okay, and that's going to give us, as soon as we do this in our calculator, 0.874 moles of N2. Now we do the same thing for oxygen. So we have 28.0 grams O2, okay, which has a 32.00 gram molar mass per 1 mole. And that is going to give us 28.0 divided by 32, a 0.875, so very similar or almost identical moles of oxygen. So now what do we do from here? Total pressure is going to be for all species, so we need to add these two together, plug that into PV equals nRT. So we're looking for P total, volume is 5 liters. Our N is going to be the combination of the 2 gases, so with proper sig figs, we end up with 1.75 essentially. Okay, and that is moles. R is 0.0821, and of course our temperature is already given to us as 298, and I apologize that just went into that problem, but that's okay. All right, partial pressures, or total pressure, excuse me. So we solve it, 1.75, 0.0821 times 298, and that's all going to be divided by 5 to isolate our P, and we're left with a total pressure of 8.56 ATMs. So pretty straightforward and pretty easy for us to do. From here, the temperature of the gas mixture in the cylinder is decreased to 280 Kelvin. Calculate each of the following. Okay, so notice the temperature here versus the initial temperature of 298. Is a change in temperature going to affect our pressure? Think about that for just a second, and let's continue on. First thing it asks about is a mole fraction of N2. Remember, a mole fraction is the moles of the thing we're looking for over the total moles in the reaction, or in the container in this case. So we are going to end up with 0.874 divided by a total moles of 1.75. And that's where we can actually leave it. We don't have to solve it, but if you want to, you get about 0.50 if you want to actually go through and do that math. Okay, just so we can kind of see what's going on. From there, we're going to calculate the partial pressure. Okay, well, remember our partial pressure equation is the partial pressure of nitrogen is going to equal the total pressure times our mole fraction, which we'll call xN2 for right now, just because it matches what is on our formula sheet. Okay, well, here's the problem. Total pressure. Total pressure is no longer 856 or 8.56. It has changed because our temperature has changed. So how do we get our total pressure? You can do it one of two ways. You can plug it back into PV equals nRT, we can recognize that the cylinder is not changing, and we can use one of our regular gas laws, which is just going to be our pressure divided by temperature. I believe this is Guy-Lussac's if I remember correctly. And pressure over temperature, so P1 over T1 equals P2 over T2, and you can solve it that way. Or you could set up a ratio, which is basically what this just did. So there's a couple different ways. I'm personally partial to PV equals nRT. It's just what I'm comfortable with, but you can do it either way you want to do it. So I have pressure times a volume of 5.00 liters. My total moles, and a technicality, this actually is easier than using this. I could put my moles of nitrogen in here and get my pressure for nitrogen only, but we'll do it this way just so we can kind of see how that works. Whatever your mole value is what your pressure is going to be. So if I have my total moles, I'm calculating total pressure. If I have moles of one species, I'm only calculating the partial pressure of that one species. So I could very easily plug in 0.874 here and get my pressure for just nitrogen. But I'm going to do it the other way just to be a button to make you use this equation. Okay, times 0.0821, and our temperature is now 280. So what do we get? We get 1.75 times 0.0821 times 280 divided by 5. And our new pressure in the system, our new total pressure in the system anyways, is going to be 805. Not done yet. Okay, from here we plug that back into our equation with our partial or our mole value up here. Okay, so up here we get, just jumping up here, the pressure of N2, the partial pressure of N2, is going to be equal to the total pressure of 8.05 times the mole fraction, which is essentially 0.50, so we'll just grab it from there. And we get the partial pressure of N2 to be, with all proper sig figs accounted for, 4.03 is what we'll call that, okay, with proper sig figs. Now, watch what happens if I was to go down here and fill this in with 0.874 for the moles of just nitrogen, and I take 0.874 times 0.0821 times 280 divided by 5, guess what I get? About 4.02, which is essentially the same thing we just calculated. So either way will work. Obviously, the first way is a lot longer than the second way, but it just kind of depends on how your brain thinks through material. Okay. Last but not least on this problem, if the cylinder develops a pinhole-sized leak and some of the gaseous mixture escapes, would the ratio of N2 to O2 in the cylinder increase, decrease, or remain the same? Justify your answer. So, pinhole-sized leak, we have to recognize what's going to happen here. Well, the gases are going to escape, okay, which they tell us. That escape, is it going to be an even escape? Are nitrogen and oxygen going to escape at equal rate? The answer is no. Here's the reason why. Nitrogen has a molar mass of about 28. Oxygen has a molar mass of about 32. They're both at the same temperature, so kinetic energy is the same for both of them. And that equals 1/2 times mass times velocity squared. So nitrogen has a lower mass, therefore it's actually going to be moving at a faster rate, whereas oxygen has a higher mass and will be moving at a lower rate, or velocity. This helps us kind of understand what's going on. Nitrogen is going to escape much quicker, so this number is going to decrease at a much faster rate than oxygen is. Oxygen is still going to decrease as well, but it's going to decrease at a smaller rate because it's not escaping quite as quickly. So what actually happens to this ratio? This ratio, which is nitrogen to oxygen, so this particular fraction, is going to decrease. Okay, and that's because nitrogen is escaping at a much faster rate than oxygen is. Okay, so hopefully we are finding these helpful. Feel free to, once again, email me. And remember, email me will be on Canvas, specifically on the discussion board we have set up going on right now, as well as sending me a remind message. If you email my school email, I will probably not see it and will not respond. Hope you guys are doing well. Miss you, and we'll talk later.